Yeah, what we do in calorimetry is we measure heat and temperature changes. That's what we're going to do. And so we're going to do three processes, three reactions in this case. Reactions, let me copy those. In one physical process here. And experiment one. Is going to be the determination of the heat capacity of the calorimeter. All right, our calorimeter, the way it's set up, it's just styrofoam cups. We're going to put two styrofoam cups here. We'll have a plastic lid, and we can put it in a beaker just to stabilize it so it doesn't tip over. And then we're not going to, this is the old setup. We have a new setup where we're using these vernier little handheld devices. And so the inputs for the vernier, I mean this is vernier, but this is the vernier CBL system where you have to connect a calculator to it, but we don't have to connect a calculator, it's standalone. And so actually the setup is pretty straightforward, so we'll just go through it together. And then we have a thermometer, but this thermometer is called a thermocouple, and the thermocouple has two different metals in there, and it measures the temperature dependence of the electrical conductivity between the two metals, and then you can calibrate that to temperature. And so our temperature probe is going to be stainless steel encased thermocouple. The thermocouple's in here to prevent it from corrosion. So we're going to use this as our temperature monitoring device. All right, so this is the basic setup of the calorimeter. So we have some kind of object or process that happens inside the coffee cup, then we can measure the temperature changes. Now if we calibrate everything, then we can figure out how those temperature changes relate to heat energy, that is joules. So this is just talking about the first law, systems and surroundings. Whatever loses, the other gains. This is talking about the object. So normally when we think of objects, we might think of gold or lead or something. And there we might be interested in how much it weighs, that is how many grams. But are we going to weigh our apparatus? No. We're not going to weigh the beaker, we're not going to weigh the styrofoam cups, we're not going to weigh the thermocouple, we're not going to weigh any of this. In other words, we're not going to get the specific heats of any of this. I mean, we could look up this, maybe we could look up the specific heat of styrofoam and figure out how many grams of styrofoam we have, but this is too much hassle. So instead, we're going to treat this whole thing as an object. So if I dump in, let's say I dump in 1,000 joules of heat. If I dump in 1,000 joules of heat, how much does our calorimeter's temperature increase? Okay, so that's the first step. The first step is to calibrate the calorimeter. And so this is why this particular equation here, Q is equal to C delta T, what happened to the mass? What happened to the mass is we're not longer dealing with mass, we're dealing with just a calorimeter, and so we have one calorimeter here. And so the amount of heat that we dump into the calorimeter will cause a temperature change, delta T. And that temperature change is going to depend on the heat capacity of the calorimeter. So C is the heat capacity of the calorimeter. And so what kind of temperature change do we expect? Well, it depends on how well insulated this calorimeter is. If this calorimeter is pretty well insulated, then the temperature might increase a lot. But let's say lots of heat leaks out. If a lot of heat leaks out, is the temperature going to increase very much? No, if we can. So it depends. So this is our lid. How good is the lid at keeping the heat in? Well, not bad, maybe. but probably not so great either. You know, eventually, if you have a hot cup of coffee, it's going to cool down. So it all depends. And so maybe some people's calorimeters are a little bit better. You know, maybe they have newer lids that aren't cracked. These ones are pretty cracked here, etc. So what we want to do is we want to figure out C. In order to figure out what C is for the calorimeter, we have to measure the heat, the quantity of heat, and so we have to have something known. Like, for example, if we have, let's say, 50 grams of water and that cools down, then we know the specific heat of water, so we can figure out how much heat was required to cool the water down. Or if we have 50 grams of water that warms up, we know how much heat is required to warm it up. And so C is going to equal the heat, so we got to figure out some way to determine the heat, and then just measure the temperature change. And so that's what we're doing today. We're going to figure out how how much heat we dump into it and figure out the temperature change. Well, we can easily figure out the amount of heat if we use water, because we know the specific heat of water. The specific heat of water is 4.184 joules per gram degree C, or 4.18 joules per gram degree C to 3 sig figs. We're going to make an assumption for this particular experiment. We're going to say that the specific heat of water is 4.18 joules per gram degree C, which is about equal to the specific heat of the solutions. The solutions that we're going to work with today are going to be, or not today, next time. The solutions that we're going to work with next time are fairly dilute. This is not 100% correct. It's just, but it's very close. And so we know this is correct. But can we say it's the same as a solution? Well, solution has other stuff in it, and so maybe not. Depends on what's in it. So let's set up the experiment. This is how we're going to figure out how much heat is dumped into the calorimeter. The way we're going to figure out how much heat is dumped in the calorimeter is we're going to have hot water. And the trick is, if you have hot water in a styrofoam cup, even if it's a double-walled styrofoam cup, so I have 2 styrofoam cups here. Even if I have 2 styrofoam cups and this plastic lid, is the water going to stay hot, or is it going to immediately start cooling down? It's going to immediately start cooling down. And that presents a problem, because let's say I want to pour water in from one cup to another. You know, with each passing second, it's getting colder and colder. And so what we're going to do is we're going to monitor the cooling curve for water. So initially I have some hot water over here at time 0. And then immediately it starts to cool down, because can we keep it hot? So for example, if I want to put a burner under here, it's going to probably start combusting the styrofoam, which we don't want. It'll start to stink up the lead. So we're going to have hot water, boiling hot water on the plates there. And then we're going to take the boiling hot water and then pour it into the cup. Is it still boiling? No, it's going to be a lot colder. And then, you know, it's going to cool rapidly, because initially when we pour it through the air, it's going to cool, and then when it hits the cup, it's going to cool. And then we're going to put the lid on there. And then it's probably going to start to cool slower. And so at time 0 here, we're just going to pour the water into the cup and then just monitor the temperature of the water. There's a hole here in which I'm going to put the thermocouple probe, which is this here. It's stainless steel. Stainless steel is very unreactive chemically, so it's good. And we'll just put this in here and then just monitor the temperature of this. Normally we have this submerged. Sometimes we don't have it touch the inner wall of this, because sometimes there's a thermal difference, although it should be the same. But you could hang these cords. Some people just hang these cords up on a utility clamp on a ring stand. But if we put this in a beaker, it shouldn't fall over. Something like that. All right, so we take our boiling water, we put it into the styrofoam cup, and then we watch how quickly it cools. And so we're going to watch the cooling curve of this. And so what's going to happen is it's going to start cooling immediately. And then we're going to monitor the cooling curve. The cooling curve should be a nice cooling curve. There shouldn't be any jumps in it, right? All of a sudden it shouldn't, like 2 minutes in, fall or rise. It just should continuously cool. And this is called Newton's law of cooling. And so we just cool it, the equation describing the cooling is Newton's law of cooling. So as it cools down, we'll just follow the trend. It might be linear like this, but it isn't linear. It's non-linear. So this kind of looks linear. There's some scatter due to random error. But anyway, we'll just watch it cool. Once we have enough data so we see how it's cooling, then we can do this. Because we want to know what the temperature is at the time of mixing. Okay, then we're going to have 2 cups of water. 1 cup is going to be, how many milliliters was it? 50 milliliters? 1 cup is going to contain 50 milliliters of hot water. Okay, that's in here. I'm monitoring the progress of that. And then I have another cup that's going to contain 50 milliliters of room temperature water. And so I'll get my, let's say 50 milliliters of room temperature water in here. And then I'm going to monitor this. Now the room temperature water might not be room temperature because it's in the pipes underground. So it might be a little colder than room temperature. And so the room temperature water might be at room temperature, in which case it'll just be flat lined, or it might be a little bit colder. If it's a little colder, it's going to warm up a little bit. But whatever it is, we want to monitor the temperature of the cold water. And so all we're going to do is we're going to take 50 grams of hot water and 50 grams of cold water and mix them together. What's going to happen when you mix 50 grams of hot water and 50 grams of cold water? You're going to get the hot water is going to cool down and the cold water is going to heat up, warm up. And so we're going to get 100 grams of mixture. And so the problem is we need to know the exact temperature at the time of mixing. And the way we're going to do this is we're going to pour the cold water into the hot water. So if we pour the cold water into the hot water, it's better than pouring the hot water into the cold water. If we pour the hot water into the cold water, it's going to cool down immediately when it hits the air here. And then it'll cool down inside the cup. And so we'll lose too much heat. And so what we're going to do is we're going to quickly remove the lid to the hot and then pour the cold in immediately and then seal it again. So this is different than the procedure. I think the procedure says to mix the hot water with the cold. Is that correct? Uh-huh. Room temperature. Room temperature is the cold water. What does the procedure say? To mix the hot water with the cold or the cold water with the hot? Cold water with the hot? Yes? All right, we're going to pour the cold water into the hot water, which makes the most sense. Situation is this. When you mix them together, how long does it take to mix the cold water with the hot water? It takes some time, right? It doesn't mix instantaneously. So as soon as you mix the cold water and the hot water, you'll have hot spots and cold spots, and eventually it'll reach an equilibrium. And so initially, when you mix it, you might hit a hot spot or a cold spot, but eventually it'll be completely mixed. And so the initial data here is going to be scattered. So you might hit a hot spot, you might hit a cold spot, but eventually it will settle and it'll be completely mixed. And then once it's completely mixed, the warm water will just cool down. All right, the reason we're going to monitor it like this is because we need to know the time, at the time of mixing, which is 6 minutes here. At 6 minutes, what would the temperature have been? Because at 6 minutes, the probe, I mean, we're removing stuff, and the probe for the cold water is removed, so we can pour the cold water into here, and then we don't have the temperatures here. We do have the temperatures because the probes don't stop recording the temperature. Because we'll just set up an experiment in our LabQuest system here. This is the LabQuest. And so we can tell the LabQuest system to collect temperature data every minute. And so the temperatures here are unreliable. And the initial temperatures here are unreliable. And so what we do is we look. Once we have the cooling curve, then we can back extrapolate and figure out what would the temperature have been if we could have mixed it instantaneously. What would the temperature have been of the hot water right at the instant mixing, and what would the temperature have been of the cold water at the time mixing? So what we have here is we're going to forward extrapolate this, and back extrapolate this to determine these temperatures. And so we're going to collect a lot of data just to determine 3 temperatures. The temperature of the hot water, the temperature of the cold water, and the temperature of the mixture. But we're going to collect lots of data. Does that make sense why we're collecting so much data? It's because the temperature is always changing. All right, what are we going to do with this data? Okay. So this is what we're going to do with this data here. So we have our hot water in here. And then we're going to, this is the hot water and what we call the hot calorimeter. And the calorimeter is going to include the probe and everything else. So when we look at the T hot, what is hot here? We have 50.0 grams of hot water plus the hot styrofoam cups plus the air that's trapped in here plus the lid plus the probe, temperature probe, plus the rest of the universe. What we're going to do is we're not going to weigh each of these things out. That's impossible. What we're going to do is we're going to take this whole thing and call it one gigantic object. Well, it's not so gigantic. If you include the rest of the universe, of course it's gigantic, but if you look at the rest of it, it's not super big. Because we've got the probe and then the lab air and then the bench and the beaker, etc., etc. We're going to call this the calorimeter. And so what is hot? What is hot is just equal to the 50.0 grams of hot water plus the calorimeter. That's what's hot. And then to this, we're going to pour in our cold water. This is going to be a 50.0 grams of cold water. Then there's going to be heat transfer. What's going to happen to the cold water? The cold water, well, let's see. It's going to be 50.0 grams of H2O liquid at, well, let's say I monitor the temperature, and at the time of mixing, it came out to 23.8 degrees C. 23.8 degrees C. And then this is going to warm up. It's going to go to 50.0 grams of water at the time of mixing, the temperature is 35.7 degrees here. Was there any change in potential energy? No. All this change is in the form of heat transfer. So Q is equal to mc delta T here. Our object warmed up. Our object is 50 grams of cold water. And so we could calculate the amount of energy here. M is 50.0 grams. C is 4.18 joules per gram degree C. And delta T is T final, 35.7, minus T initial, 23.8 degrees C. So the grams cancel, the degrees C cancel, and that leaves us with joules. So we can figure out how many joules of energy the cold water must have absorbed. So let's go ahead and do that calculation. It's going to be 50 times 4.18 times, what is that, 35.7 minus 35.7 minus 23.8. I get 2,487.1 joules. This is too many sig figs, but I'm going to just retain them till the end. So where did all the heat come from to warm up the cold water? So what must have cooled down in this case? The hot water. But not just the hot water. What else was hot? The calorimeter. And so over here we have our hot water plus calorimeter. And we know from the first law of thermodynamics, if our cold water absorbs this much, our hot water must have lost that much. And so the hot water Q must be equal to minus 2,487.1 joules. So we know how much energy the hot water and the calorimeter lost. So we're going to have 50.0 grams of H2O liquid at 48.4 degrees C. That's a hot. 48.4 degrees C plus calorimeter at 48.4 degrees C. And then this is going to cool down. So we're going to end up with 50.0 grams of water at 35.7 degrees plus the calorimeter at 35.7 degrees C. So we know that Q, the amount of heat this whole thing has to have lost is minus 2,487.1 joules. I can do this all in one equation. I'm going to do it in 2 steps here. And that's going to equal the amount of heat that was lost from the hot water plus the amount of heat lost from the calorimeter. The amount of heat lost from the hot water, we can just use Q is equal to MC delta T. So it's MC delta T for the hot. And the amount of heat lost by the calorimeter is, how many calorimeters do we have? 1. So we have 1 calorimeter times C times delta T of the calorimeter. This is going to be C of the calorimeter. This is going to be C of the water. Usually people don't write 1 here, and so it's just C of the calorimeter times delta T. There's no reason to weigh it. It would be impossible to weigh the rest of the universe plus that. All right, so what we're doing is we're calling our system this. And then this is our surroundings here. To make them equal, we change the sign. So that's why I changed the sign over here. It's negative. So the only unknown here is going to be C of the calorimeter, because we know the mass of the hot water, it's 50.0 grams. We know the specific heat of water, 4.18 joules per gram degree C. And we know delta T of the hot water is just the T final, which is 35.7, minus T initial, which was 48.4 according to our graph. Degrees C, plus C of the calorimeter times delta T of the calorimeter. Delta T of the calorimeter is the same as the hot water because it's in thermal contact. So it's going to be 35.7 minus 48.4 degrees C. Okay, and this whole thing has got to equal minus 2487.1. So I'm going to go ahead and let's calculate it here. Actually, let me get rid of that. So 24, I'm just going to subtract minus parentheses 50 times 4.18 times 35.7 minus 48.4. 35.7 minus 48.4, close parentheses. 5141. So I get 51. Oops, did I do negative? Shoot, I didn't. That's wrong. Minus 2 times 2487.1. 167.2. So I get 167.2. The units here are going to be in joules. Everything else cancels out. Is equal to C of the calorimeter times delta T. So I'm going to do the delta T. 35.7 minus 48.4 minus 12.7. Let me make sure I did this correctly. Oh, I know. I need to do one thing. The sign convention here, we have to be careful with, because of this. So this would be a negative. This is going to be the negative over here. And so I forgot to put the negative sign over here. And so this is going to be a negative times a negative, which is going to give us a positive. And so I'm going to invert this times 167.2. And I'm going to get C of the calorimeter is equal to plus 13.165 joules per degree C. How many sig figs am I allowed for this? Looks like we're probably okay with 3 sig figs, it's looking like. So maybe we'll just round this to 3 sig figs. At 13, 2 or 3 sig figs. So 13.2 joules per degree C. So there is some heat that leaks out of this. In other words, this is not a perfect insulator. If this was a perfect insulator, it would absorb no heat. But what happens is, to warm this up, it would be 0. If this were a perfect insulator, it would be 0 joules, because it would just warm up to whatever temperature you're at without it absorbing any heat. But there's some heat lost through here, so we're going to have just 13.2 joules per degree C of heat lost into the calorimeter. Or absorbed. In this case, heat was absorbed by the calorimeter. And so we have the, or no, lost. Actually, heat, anyway, absorbed, lost, maybe, I'll set up the other equations differently. But this one, we can think of as the cold water absorbing, and then the hot water and the calorimeter losing. So we're going to lose some heat from the calorimeter as well. All right, any questions on this? So this is what we're doing today.
Can you scroll up a little bit? Oh wait, sorry.
Here?
Yeah.
The sign, you know, I should have done this in one equation, and then here. It's just because this negative sign that we assigned to the surroundings. So Q of the system is equal to negative Q of the surroundings. And so I changed the sign on this. This was absorbed, this is released. But I forgot to change the sign on this. This has got to also be changed. So sometimes it's helpful just to put it in one big equation, which I'll do for the next one. All right, so today we're going to set up this so we can collect data here, like this. All right, that's experiment 1. In experiment 2, what are we doing? We're taking hydrochloric acid and sodium hydroxide solution. And so let's take a look at experiment 2 next. So in experiment 2, we're going to be monitoring the 2 solutions here. What are we going to pour? Are we going to pour the acid into the base or the base into the acid? Acid into the base? Is that what the instructions say? Okay, that's... How much hydrochloric acid are we using? 50.0 milliliters of hydrochloric acid. What's the molarity of the hydrochloric acid? 1.05 molar. In the other coffee cups, this one we'll call our calorimeter. We've calibrated this one. This one should be close, but because the lid's different and other things, it might not be exactly the same. So this is going to be our calorimeter. In our calorimeter, we're going to have 50.0 milliliters of sodium hydroxide. And what's the concentration? 1.00 molar. So can you look at this and tell me what the limiting reagent is? What do we have more of, the hydrochloric acid or the sodium hydroxide? We have more of this, so this is called the excess reagent. And this would be our limiting reagent, LR. How many moles is this? So we can figure out how many moles of sodium hydroxide react. How many moles of sodium hydroxide react? We just multiply these two. Volume times molarity gives us the moles, and this is going to be 0.0500 moles. 0.0500 moles of sodium hydroxide react completely. When mixed. So we're going to do this. We're going to monitor the temperature of both. Both of these should be at the same temperature. And so channel 1, channel 2, or whatever. And then we're going to monitor over time to make sure it's stable. And then at minute 6, what are we going to do? We're going to mix them at minute 6. And what's going to happen is we're just going to watch what happens when HCl reacts with sodium hydroxide. When HCl reacts with sodium hydroxide, this is an exothermic reaction. So HCl plus sodium hydroxide is going to make what? Sodium chloride and water and energy. Hydrochloric acid is higher in chemical potential energy. Sodium hydroxide is higher in chemical potential energy. And so we're just going to monitor this in terms of chemical potential energy. So this is a process here. And so we're taking hydrochloric acid and sodium hydroxide, which is a higher energy mixture, and allow that to react at RT. We're going to allow that to react to form sodium chloride plus water, which is much more stable and unreactive. This is going to be at RT. Was there any kinetic energy change here? No. And so Q is Q of reaction. Can we use the equation MC delta T? Would it work here? No, because we're not cooling an object. We're not warming an object. This is not MC delta T. This is just Q of the reaction. And this is going to be Q of our system. And this system is going to dump heat into the surroundings. So this is going to be equal to minus Q of the surroundings. So what we want to do is we want to measure Q of the reaction. How much heat is dumped into the surroundings? So all we have to do is monitor the temperature of the surroundings to figure out how much heat is dumped into the surroundings. And so what we're going to do here is we're going to mix the acid into the base at T equals 6 minutes. And then what's going to happen is this. Let's see if I have a curve here. No, I don't have the curve. So the graph is going to look like this. This will be the output data from your, actually you'll have a table, and then we can graph it. So this is temperature versus time. Both of these should be at the same temperature. So we monitor, and hopefully they're both at the same temperature. However, they could be off a little bit due to calibration. Okay, when you mix it, what's going to happen to the temperature? When you mix it, let's follow the blue here. When we mix it, the temperature jumps up. But it might, depending on if we hit hot spots or cold spots, the first or initial data might not be reliable. And so we look at the latter data, and then what we look at is we look at the cooling curve of the mixture here. And we back extrapolate this to 6 minutes. So this is going to be T of the mix. And then down here we'll have T of the HCl, and we'll have T of the sodium hydroxide. And so all that heat was dumped into the mixture here. So Q of the system, which is equal to Q of the reaction, this is the HCl plus sodium hydroxide yields NaCl plus H2O plus energy. So where did that energy go? That energy went into the surroundings. So this is going to equal minus Q of the surroundings. So we got to figure out what is our surroundings here. Our surroundings is everything left over after the reaction. Everything left over after the reaction. Has completed. So does it take very long? No, it doesn't take very long for a strong acid to neutralize a strong base. It's pretty quick. And so once that reaction's over, what's left over? What's left over is salt water. How much salt water do we have? We have 100.0 milliliters of salt water because we took 50 milliliters of acid plus 50 milliliters of base. We're going to get 100 milliliters of salt water. That's what's left over. the salt water was a product of the neutralization reaction, but once that reaction's done, then that's the remnants of that. What else is left over? The rest of the universe. Well, the rest of the universe we call the calorimeter. So we're going to have Q of the reaction. This is for a reaction of 0.0500 moles of sodium hydroxide. Energy is extensive, so the more sodium hydroxide we neutralize, the more heat we're going to generate. And then this is going to equal minus Q of the surroundings. Which is equal to minus, okay, the salt water. The salt water is going to be M. M is going to be, well, what's the density of salt water? We have 100 milliliters of salt water, but it's salt water. It's not pure water. And salt water should be slightly more dense than pure water because we got salt dissolved in the water. But it's very dilute. Since it's very dilute, we're going to assume that it's close enough to pure water. And so what we're going to do is we're just going to assume that its density is the same as water, or close enough. The density of the salt water is about equal to the density of pure water. And so that's going to tell us how many grams of salt water we have. What else do we need? We need the specific heat of salt water. There's a problem though. I don't have the specific, actually, we could look it up. But you know, the salt is so dilute that we're going to just make another assumption. We're going to assume that the specific heat of the very dilute salt water is close enough to pure water. And then we need delta T. Well, delta T is not difficult because we're going to be monitoring the temperature. And so delta T is going to be the time of mixing here, the temperature at the time of mixing here. This will be our delta T. Plus, how many calorimeters do we have? Just one. Times the heat capacity of the calorimeter. This is from experiment 1. Times our delta T of the calorimeter. Delta T of the calorimeter and delta T of the salt water are the same. So this is delta T of the salt water and calorimeter. And then we're going to make a calculation. The heat of reaction is often called a delta H. This is delta HR, heat of reaction. And so what we're going to do is we're going to take the heat from here in joules divided by moles. And then it's going to come out too big, so we're going to go kilojoules per mole. And so all we're going to do is we're going to take the heat that we calculate and divide it by 0.0500 moles. And then we'll get this. So this is extensive. This is going to depend on how much. But the heat of reaction is intensive because it's normalized per mole. And so it depends on how many moles. But it's a ratio. And so it would be intensive. And so in part, experiment 2 of this, we're going to determine the heat of reaction of HCl and sodium hydroxide aqueous. Let's take a look at reaction 2. When we look at reaction 2, this is a physical process. And so this is called dissolution. So what you're going to do is you're going to get some solid sodium hydroxide. Sodium hydroxide is a pain to work with because it's hygroscopic. You have to weigh it dry. Hygroscopic means it absorbs water or moisture from air. And so if you're to weigh it, the mass just keeps climbing, climbing, climbing. So we'll just weigh it right out of the desiccator. You bring a watch glass like this, they'll plop a sample on here and tell you how much it weighs. And then you bring this, you cover it, and you bring it over to your table. You cover it so it doesn't absorb too much water. You get this right before doing it. And then you'll scrape it in. When you scrape it in the water, it dissolves. And this process is exothermic. And so it produces energy. Some dissolution processes are exothermic, like this. Some are endothermic. This one's pretty exothermic. It releases a lot of energy. And so where does all that energy go? So when we dissolve the sodium hydroxide in water, where does all the energy go? It goes into everything that's left over after you dissolve the sodium hydroxide. So what's left over? Well, what's left over is going to be sodium hydroxide solution and the calorimeter. That's what's left over. And so all this energy, this is going to be Q of the system. Q of the system is equal to Q of dissolution is equal to minus Q of the surroundings. Now the surroundings consist of the sodium hydroxide solution that's left over plus the calorimeter. So in order to figure out the sodium hydroxide solution, we need to know the mass of solution times the specific heat of the solution times delta T of the solution. Plus, we only have one calorimeter, so we just need this heat capacity of the calorimeter times delta T of the calorimeter. But delta T of the calorimeter is the same as the solution since they're in thermal contact. Now the mass of the solution we're going to calculate a little differently here. The mass of the solution is we're going to have 50 grams of water. Is that correct, or 100 grams of water? I think it's 50 grams of water. So we're going to have 50.0 grams of H2O plus from the stockroom you're going to get X.XX grams of sodium hydroxide. So we're going to have 50X.XX grams of solution. So here we're not going to assume anything about the density. Oops. Okay. Something like that. So we do a very similar calculation here. That's for this. Reaction 2 here. And then we can figure out what Q of dissolution is. You know, we can figure out how many moles. And then we can get delta H of dissolution. Delta H of dissolution, which is a physical process, or dissolving, is just equal to Q of dissolution divided by the moles of NaOH. 1 gram is, or 2 grams is not that many moles. It's like 0.05 moles or something like that. All right, then we're going to do reaction 3, in which we're going to take some solid sodium hydroxide and mix it with hydrochloric acid and figure out this. And so this is going to be a reaction. So Q of the reaction is going to equal minus Q of the surroundings. Our surroundings are going to be, in this case, the product mixture. That is the salt water plus the calorimeter. And so we'll do a very similar calculation here. The salt water will do the same as reaction 1, except we have less. Actually, sort of the same. We're going to have, you know, y grams sodium hydroxide here plus 50.0 milliliters. So we'll call the 50.0 milliliters about 50 grams. And so this will be 50 y grams of salt. Something like that. Or, I don't know. Or just follow the book, whatever the book says. Okay, then we're going to get this. We're going to get delta H for reaction 3, which is going to be equal to Q of the reaction divided by the moles of the reaction. Here, we need to know what the limiting reagent is. So that's going to tell us how many moles of reaction we had. And so first thing is, before doing this, we need to determine what the limiting reagent is. And so this will be per mole of LR, limiting reagent. All right, any questions on this here? So reactions 1 through 3 we're going to do next week. Today we're going to do the calorimeter. So you're going to work with a partner or partners, maybe up to a group of 3 again. And then we're going to have this. Go check out your calorimeter and the Vernier LabQuest system. And then we'll set it up together. At least I'll show you how to set up the Vernier. Before you check that out, or while you're checking that out, the other partner gets some water. Use DI water. Put it in a big beaker and start heating it up. You need 50 milliliters. But boil more than 50 milliliters. It doesn't have to be a big beaker, just some beaker. Goggles aren't required. Today's just water, so. So just continuing on here, the equation for cold water warming is, does it depend on how much water you have? How much energy it takes to warm up water? Does it depend on how much you have? So if I wanted to warm up a liter of water, it takes exactly the same amount of energy as 10 liters of water, or does 10 liters of water take more energy than 1 liter of water? It takes more energy. Energy is extensive, so we need to know the amount, and the amount is in mass. and then we warm it up to a certain temperature. That temperature is going to result in a delta T. And so what do we need to relate mass and delta T? We need C. What was C called again? The specific heat of water. Most people have it memorized, 4.18. The reason most people have it memorized is because it's the same as the joule to calorie conversion. And therefore most people already have it memorized because 1 calorie is the amount of heat required to raise 1 gram of water by a degree C, so that's 4.18 joules. This is equal to how much energy did it take to cool down? And so the hot water cooled down, how much energy does that take? It takes, well, how much hot water do you have? So it's the mass of hot water times C, the specific heat of water, times delta T. It's the same thing. But what about the calorimeter? How many calorimeters do you have? Do we measure how many grams a calorimeter weighs? No, how many calorimeters do we have? 1 times C of the calorimeter times delta T of the calorimeter. Delta T of the calorimeter is the same as the delta T of the hot because they were both hot and then they went into the mix. So this equation is different than the equation in the lab manual because we added the cold to the hot, not the other way around. And it works a lot better if you add the cold to the hot because we don't have to worry about losing heat to air when we pour the water from the styrofoam cups. So anyway, you should learn how to derive an equation like this. See if you get a reasonable number. Can you guys return the equipment? We don't have enough time to repeat it anyway, but just go ahead and return the equipment to the stockroom. And then try to get a calculation for the calorimeter.
So with the delta T for the cold water, or I guess for all of them, is it going like it's the temperature at 15 minutes minus 1, or at 5 minutes minus 1?
No, at 6 minutes, not minus 1. If we don't care about any of these temperatures. These temperatures aren't the temperature at which they were mixed. This is delta T hot here. This is delta T cold here. The hot is both for the hot water and the calorimeter. The hot water and the calorimeter are in what we call thermal contact with one another. So the hot water and the calorimeter are the same. And so this hot curve here is the hot water plus hot calorimeter. And this bottom curve here is just the cold water. So what's going to happen is the hot water and the hot calorimeter are going to warm up the cold water. In that process, they're going to cool down. We did all this graphing only for 3 temperatures. That's all we're trying to get is 3 temperatures off this. The one circled in black. That's why I want to see your graph. I want to see what the 3 temperatures are that you got. But yeah, can you return the equipment now and then Yes.
about the initial and final. So on the graph, we write at 5 minutes the temperature, and 2 minutes later we write that.
Yeah.
So, but from the tablet, we're able to calculate.
The tablet, though, it gives you the temperatures at 6 minutes, but they're incorrect.
They're incorrect.
Yeah.
Okay.
Okay, that's a good point. These temperatures marked in black here are not the temperatures of the probes. We have to ignore the temperature at 6 minutes from the probes because those aren't telling us the accurate temperatures. Therefore, we have to do extrapolation. Extrapolation just means kind of backtracking or forward tracking this. What would the temperature have been if we just follow the smooth curve? So there's forward extrapolation here, and here, and back extrapolation here. We just work backwards to figure out what the temperature should have been. As the whole reason we're doing this is because we can't measure it. It doesn't mix in one instant of time. It takes time for it to mix.